Welcome to Power Electronics Education Electronic Book, Lecture 6, Non-Isolated DC-DC Converters with Real Components. This lecture is presented by Dr. FIRUZ ZARE. In Lecture 5, we study different types of DC-DC converters with ideal components. Now here we are going to look at the converters with practical or real components. That means, for example, we consider the internal resistor for the power supply, and also we consider the switch not as an ideal switch. That means the voltage drop across the switch can be defined as a DC source and also in series with the resistor. When diode conducts, we also consider voltage drop across the diode in series with turn on resistor. Also we consider the resistor in series with the inductor, which shows the losses. So similar to analysis in chapter 5, we can consider when the switch is on and off. For example, when the switch is on, so in this case diode is off, but here we consider the voltage drop across the switch and also turn on resistor. So it depends on the switch. For example, if you have MOSFET, we can ignore the voltage drop, just consider the turn on resistor. Or if we have IGBT, we can just consider the voltage drop. When the switch is off, so in this case diode conducts, we have voltage drop across the diode and also we consider the turn on resistor. So in this case we can write the equation for the time that the switch is on. So the voltage drop across the inductor can be found based on this circuit diagram, which is basically input voltage here equals to voltage drop across this resistor plus voltage drop across the switch, voltage drop across the internal resistor of inductor, and also output voltage, which is given in this equation. And if you look at the inductor current, basically inductor current equals to current through the capacitor plus output current, which is given here. So then we can write the equation for inductor voltage and capacitor current when the switch is on. So when the switch is off, diode conducts. Then in this case we consider the voltage drop across the diode and also we consider the internal resistor of the diode. So in this case, according to this loop, we have voltage drop across the diode plus voltage drop across RD, RL, the voltage across the inductor plus the voltage across the output. And again, the current through the inductor, IL, equals to current through the capacitor plus load current, so which is given here. And assuming that the ripple is not significant, so V out is given here. And suppose that the inductor ripple is not significant, so we have also current here. Then we can also write the capacitor current in terms of inductor current and output voltage. So here we can see that the voltage across the inductor when the switch is on and when the switch is off are given here, and this is the current through the capacitor. That means it's almost same when the switch is on and off. So in a steady state, as we mentioned, the average voltage across the inductor should be 0, otherwise the system doesn't operate in a steady state. That means this area should be equal to this area. That means the average over one cycle is 0, and is almost same for the current through the capacitor. That means the average current should be 0. So when the system operates in a steady state, the average current through the capacitor should be 0. So this is the equation. But here we can see that this average is 0. That means the DC part, inductor current, equals to voltage divided by resistor. So it's almost same scenario for average voltage across the inductor. This average should be 0. This is the equation. Again, that means this area should be equal to this area. Simple method is to find this area, which is basically this magnitude times of dts, which is given here, and this magnitude times of d prime ts, which is given here. If we simplify this equation, that means removing ts, then we come up with this equation, and this is the equation for the capacitor current. So finally we can simplify that one. That means instead of current, inductor current, we can put output voltage divided by R, which is also given here. If we move the output voltage on the right hand side and the rest of variables on left hand side, we can simplify. That means we can define this factor for Bach converter, and we can find the conversion ratio, which is basically duty cycle divided by K Bach minus this term, which is basically depends on the voltage drop across the switch, plus this term, which is basically depends on the voltage drop across the diode. So if these resistors are zero, that means K Bach equals to 1. So this equation will be d minus dvs divided by vin minus d prime vd divided by vin. So basically, if the voltage drop across the switch and diode are 0, so this is the conversion ratio for ideal case. Otherwise, we can see that this term can change the output voltage. So if you look at these equations for real components, we can see that this factor is defined by this term. So suppose that at low duty cycle, that means that this one is not significant. And even here, because these resistors are changing between 0 up to 0.1, so with respect to load resistance, even this term is not significant. So it's almost same scenario when the system operates at high duty cycle, because again, this term is not significant. So that means this factor is almost equals to 1. So if you look at this equation, conversion ratio, so basically because K is almost equal to 1, so we have this number, and now this factor is determined by Vs over Vin and also Vd over Vin. So here we can see if the Vin much more than Vs or Vd, the voltage drop across the diode or voltage drop across the switch. So here the conversion ratio is almost same as ideal component. Here we can see that when the voltage across the diode is changed between 0 and 1, or the voltage across the switch is changed between 0 and 3, we get almost same conversion ratio, except at this point, and that's because of this factor, which is significant. We can also look at the conversion ratio when the input voltage is 10 volts. So here again, same scenario is valid for this case. That means this factor for Bach converter is almost close to 1. And in this case, we can see that this conversion ratio is basically equal to ideal case, except this factor and this factor. So basically, look at the conversion ratio when the duty cycle is pretty low. If duty cycle is pretty low, that means this term is not significant, but this term is significant. So that's why here we can see that the voltage drop across the diode can change the conversion ratio when the duty cycle is low. That means d prime is close to 1. And on the other hand, when we can see that when duty cycle is high, that means d prime is low. So this term is not significant, while this term equals to 1 approximately. So that's why the ratio of Vs over Vin can change the conversion ratio. That means this factor can decrease the conversion ratio. Here we can see that when, for example, Vs is 0 or Vs is 3, so we have different conversion ratio, and that's because this term is significant. Now let's consider a boost converter. Again, in boost converter, when the switch is on, we have internal resistor of the inductor, input impedance of the supply, plus internal resistor of the switch and the voltage drop across the switch. And when the switch is off, in this case diode conducts, switch is off, again we have these components which should be considered in the steady state equation. So when the switch is on, we have this circuit diagram. We can find the voltage across the inductor when the switch is on, which is basically input voltage equals to voltage drop across these components plus the voltage across the switch, which are given here. And we can see that the current through the capacitor is minus V out over R. So this is the equation, considering that the ripple is not significant. So we can write the equation again. So when the switch is off, diode conducts, again we can write the voltage for this circuit. So basically input voltage equals to voltage drop across these components and plus output voltage. And also the inductor current equals to current through the capacitor plus load current, which is given here. And suppose that the ripple is not significant, we can write IL, and also we can write V out here because ripple is not significant. Then we can find the voltage across the inductor in terms of this parameter and the current through the capacitor in terms of these parameters. So this is basically the voltage across the inductor for the time that the switch is on and off. Same current through the capacitor when the switch is on and when the switch is off. So basically in a steady state, the average voltage across the inductor should be 0, as well as average current through the capacitor should be 0. So in this section we can find the average current through the capacitor based on this equation. So basically we need to find this integral over one cycle. Basically the current over this cycle when the switch is on is minus V out over R, which is given here, and the current when the switch is off over this interval is given here. So when we simplify this equation, then we can find that the inductor current equals to output voltage divided by d prime R. We can use this equation for steady state equation. Same scenario for inductor voltage. So the average voltage across the inductor over one cycle should be 0. That means this area should be equal to this area. So a simple way is to basically find this area, which is basically this magnitude times of dTs, which is given here, and this magnitude times of d prime ts, which is given here. When we simplify that one and remove ts, we have this equation, or we can write up the equation in terms of these parameters. That means put the variable on the left hand side and the output voltage and inductor current on the right hand side, and here we can substitute inductor current with this variable, with this equation, and we come up with this equation. So we just need to simplify this equation. Basically again we have V out times of this factor, which is basically defined as a factor of boost, and we have this term which is basically input voltage, voltage across the switch and voltage across the diode, and the conversion ratio is given here, which is basically 1 divided by d prime times of k boost minus this factor minus this factor. So for the boost converter, this is the conversion ratio, and this is the factor for boost converter. So again, here we can look at the main parameters which may change the conversion ratio. We know that at high duty cycle, these resistance may change the conversion ratio. So if we simplify this equation at high duty cycle means that D equals to 1. So then we have these three parameters divided by D prime square, while this factor is not significant. That means this factor is not significant compared to others, because at high duty cycle D prime is close to 0. So that's why this term is significant. Here we can see that the effect of Rin, RL, and RS at high duty cycle are significant, while the effect of RD at high duty cycle is not significant, and that's because of this description. That means that the K boost will be totally different compared to ideal case, and that's because of these three factors which change this factor. So if we look at the conversion ratio, so that's why at high duty cycle K boost will be different, and in this case we can see that this will be the conversion ratio, and because K will be significant, this term will be pretty low at high duty cycle for different resistors. And if you look at these factors, for example the effect of voltage drop across the switch or the effect of voltage drop across the diode, so again we can see that VD over Vin, especially for 100 volts, is not significant. So that's why we can ignore this term. At high duty cycle, this term compared to this term is not significant, because dVs equals to approximately Vs, and Vs divided by Vin is not significant. So that's why this is the main factor to define the conversion ratio for boost converter with ideal components. We can also look at the conversion ratio when the input voltage is 10 volts. So in this case, again, this factor is not significant. That means the voltage drop across the diode cannot change the conversion ratio significantly. But here we can see that because at high duty cycle D is almost equal to 1, so D prime is significant. So D prime is small, but 1 over D prime is significant. So that's why if the input voltage is low, so this term may change the conversion ratio at high duty cycle, and here we can see that it has effect on the conversion ratio, and that's because of voltage drop across the switch. Now let's consider a Bach boost converter. Basically in Bach boost converter, again when the switch is on, we have these parameters to model the switch, and we have input impedance of the power supply and also internal resistor of the inductor. When the switch is off, diode conducts. So in this case we have these parameters to model the diode. So when the switch is on, we can write the equation. Basically input voltage equals to voltage drop across these components plus the voltage across the inductor, which is given here. And in this case the capacitor current equals to minus I out. Suppose ripple is not significant, then we can rewrite the equation again here. So when the switch is off, in this case diode conducts. So basically this is the diode which has been modeled as a voltage source and this internal resistor. So we can actually write the voltage for this loop. This is output voltage, plus the voltage drop across the diode, which is written here, and also voltage drop across the inductor, which is written here. And in this case, the current through the inductor equals to current through the capacitor and load current, which is written here. And suppose that the ripple is not significant, we can rewrite the equations here. So now we can simplify the equation. That means the voltage across the inductor over one cycle is given by these equations when the switch is on and when the switch is off. And the same for capacitor current when the switch is on and when the switch is off. So in order to find the steady state equations, we need to find the average voltage across the inductor and average current through the capacitor. So now we can find the average current through the capacitor according to this equation. We have the current through the capacitor when the switch is on and when the switch is off. So average over one cycle is 0. That means this average should be 0. When we simplify the equation, we can find the output voltage in terms of duty cycle and inductor current. And when we simplify, finally we can find the inductor current in terms of output voltage, duty cycle, and load resistor. We can also find the average voltage across the inductor. That means this integral should be equal to 0. In this case, this average, this area should be equal to this area. So in order to find this integral, the easiest way is to multiply this magnitude by this time, which is given here, and this magnitude by this time, which is given here. And when we simplify this equation, we end up with this one. And finally, we can simplify the equation in terms of output voltage and inductor current. And on the left hand side, we have input voltage, voltage across the diode and switch. And when we put the inductor current in this equation, then we can find the conversion ratio. So basically, when we simplify this equation, which is basically given here, and when we divide by this factor, this is the conversion ratio. That means basically if these resistors are 0, this factor is 1. So basically we get almost same conversion ratio for ideal case. Now we can analyze the conversion ratio for Bach boost converter. So this is the factor for Bach boost converter. Again here we can see that at high duty cycle D is almost equal to 1. So that's why this term compared to this term is significant, because at high duty cycle this term is close to 0. So that's why here we can see that RL, RS and Rin are important factors. If you look at the conversion ratio here, you can see that the conversion ratio is affected by these variables, while here we can see that RD is not significant. So K Bach boost is an important factor to determine the conversion ratio for Bach boost converter operating at high duty cycle. So that's why this term, which is basically is the important part for Bach boost converter, and for ideal case we have d over d prime, but for non-ideal case is d over d prime times of this factor. And again here we can see that the effect of diode voltage on the conversion ratio is not significant, and the reason is that Vd over Vin is not significant, especially when the input voltage is 100 volts. And also we can see that this factor compared to this factor is not significant, because the difference is Vs over Vin, and when the Vs is 3 volts and when Vin is 100, so this factor is not significant. So that's why the conversion ratio basically is determined by this factor. So when the input voltage is changed to 10 volts, here again we can see that this factor may be significant compared to other factors, because again the voltage drop across the diode is not significant. That means this factor is not significant. But if we look at this conversion ratio with real component, the difference between this factor and this factor is this ratio, Vs over Vin. So basically, because Vs over Vin is a significant factor, because Vin is 10 volts and Vs, the voltage drop across the switch, is changed between 0 and 3 volts. So that's why this factor is important. So here we can see that the conversion ratio basically has been affected by this factor. That means when the input voltage is low and when the voltage drop across the switch is high, then the conversion ratio is also affected by the voltage drop across the switch.